Hello everybody and welcome back to the 2016 F equals MA, and we're going to be working problem 20. This test has 25 questions which increase in difficulty, and I actually got this in like a small amount of time, which is pretty good. So we have a uniform solid right prism, and this is like an incline, and so really there's a third axis here, but we're just looking at a cross section. The cross section is an isosceles right triangle with height h and width 2h, and is placed on an incline that is a variable angle theta with the horizontal. And we want to find the minimum coefficient of static friction so that the prism topples before it begins sliding as we increase theta. So a typical problem, sort of the analogous version of this, is that if you just have a mass on an inclined plane and you increase the theta, you want to find the minimum theta, or you want to find basically the relationship between the static friction and um, the angle at which the block will start moving. And I won't prove that in this video, but there's actually the coefficient of static friction mu is equal to the tangent of theta. So for a given theta, that will be sort of the minimum you need for it to not slide. So let's think about when the prism will topple. Something topples um, if its center of mass is sort of unbalanced with the rest of the figure, for lack of better words. So let's say, we have a uniform square. So since it's uniform, its center is just here, right? And we can tilt this square. Try and draw a good picture here. We can tilt the square like this. This is a 45-degree rotation. Doesn't look like 45 degrees, but just imagine you took say just like a Rubik's Cube, I guess, and you tilted it 45 degrees. At that 45 degrees mark, the center of mass is in line with sort of the point that is in contact with the ground. So if you were to rotate this any more to the right, it would topple. If you were to rotate this any more to the left, it would topple that way. So essentially the center of mass, toppling depends on where the center of mass is in relation to sort of the point at which you would topple, or like the toppling, I don't know, like this point, right, where you would flip over that point, basically the point of rotation. So if we consider an isosceles right triangle, well, for any triangle, the centroid, which is also the center of mass, is the intersection of its median and of its medians. And since we have a uniform right prism, we only need to consider this 2D case, right? So we don't need the whole 3D picture because everything will be the same for each cross section. So the centroid it would sort of be like in the middle of the right prism, but at this point. So if you took the midline cross section, you would get this, and this would be where the center of mass is. So we want to find the angle of rotation such that if I were to draw a line from sort of this lower point, right? Because as we increase theta, it becomes obvious that this point will be it will be the toppling point, as I'll call it. So we want to know for which theta will this be in line. So let me try and draw a diagram of that. Okay, so we're just gonna, I couldn't quite get the line to be in center, but I'll apply the same mathematics. So if they were in line, right? If the centroid was directly above the toppling point, which is right here, this vertex A, I'll call it A is the toppling point, then the median, right, from A would make a 90-degree angle with the ground, because if you draw a line from A to something directly above A, it'll perpendicularly hit the original line that A is on. So we have a 90-degree angle here, and I know it does not look like a 90-degree angle, but just take that for my word. And we know that, so we have this is being bisected, right? Because it's hit by a median here. And we know that this is equal to h. Well, no, that's not equal to h. But let's say this is equal to x. We know that this side is also equal to x because it's an isosceles right triangle, which means that this little line here is just half of x. So this smaller angle here, I'll call it alpha. Alpha satisfies the property that tangent of alpha is 1/2, right? Because the opposite is x over 2 and the adjacent is x. So tangent of alpha is 1/2. Well, we know that this whole angle, right? This angle right here, one of the angles of an isosceles right triangle is just pi over 4, right? And we know that the tangent of pi over 4 is equal to 1. So what is the tangent of this angle, right? Essentially, we're finding the tangent of pi over 4 minus alpha. So we can use the tangent subtraction formula. So here we have the tangent of pi over 4 minus alpha is the tangent of pi over 4 minus the tangent of alpha divided by 1 plus, and here I just wrote t, but tangent of pi over 4 times tangent of alpha. And we know that tangent of pi over 4 is just 1/2. I mean 1, right? So we have a 1 here and a 1 here. Tangent of alpha is 1/2. So 1 minus 1/2 is 1/2. And in the denominator, we have 1 plus 1/2, which is 3/2. So this angle, the tangent of this angle, is 1/3. And so and so we want to find, what we want to find is theta. And we know that theta and this angle, I'll just call it beta instead of calling it this angle. So this is tangent of beta. And we want to know what the tangent of theta is, right? Because tangent of theta will give us our minimum static friction. So here we have tangent of beta. So we want tangent of 90 minus beta, and that is actually just equal to 1 over tangent of beta. So therefore, the tangent of theta, and if you don't believe that, just try and plug in 90 minus theta into tangent of theta, and you'll see that it is actually 1 over tangent of theta. So tangent of theta is equal to 3, right? 1 over 1/3. And so that's just the answer. This is the minimum value of static friction that we need, or coefficient of static friction. So I hope you enjoyed this. I really like this problem. So thank you for watching, and I will see you in the next one.